Alright, ladies and gentlemen, I am assuming, since it's been close to a week since the time that we started this chapter, I'm assuming you remember pretty much nothing. That's probably not a very nice assumption, but realistic. Okay? So we're going to start today by basically reviewing what we did last class. I'm going to do an example problem with you, and then I'll have you do one on your own. Okay? So chapter 12, remember, it's called Kinetics. It's all about speeds of reaction. Are they fast? Are they slow? And the first major type of problem that you're going to come up against is something like this, which is you're given a table of molarities and rates, speeds, and you'll be asked to write what is called, they'll either say just write the rate law or write the rate law expression. Okay, fine. So, first thing you write, rate equals lowercase k. What do brackets mean? Molarity of your first reactant times molarity of the second reactant. If there was a third reactant, you would multiply times the third one. And the only thing that you really have to figure out is what are the exponents for each reactant. And let's just start with the first one, nitrogen monoxide. And remember, what you're looking for in this chart, we're going to start with nitrogen monoxide. You want to look and ask yourself, which two lines can I compare where the one I am concerned with, so where nitrogen monoxide's molarity changes, but the other reactant remains constant. Which two lines? Okay, 2 and 3, sounds good. So, comparing lines 2 to 3, tell me what happens to go from here to here. Multiplied by what number?
2.
Okay. The other reactant remains constant. It has to. And some of you may be able to just sort of see this. If you're not sure what it's being multiplied by, it will always be a whole number. You could always put this number divided by that number in your calculator. But what is it here?
3.
It's basically...
3.5.
No, whole number.
4.
4.
Hooray.
It might be like 3.99. Okay, it's 4. And remember, you take these two numbers, you say 2 to the what power equals 4. What do you get?
2.
Okay, so nitrogen monoxide has an exponent of 2. Let's move on to the other reactant. So that would be chlorine. Which two lines should we compare where chlorine changes but nitrogen monoxide remains constant? Okay, sounds good. Chlorine is changing. What's it being multiplied by?
2.
The other reactant is remaining constant. What's happening to the rate?
2.
Also being doubled. So what's my exponent?
1.
Okay, which you can, it's your choice. You could either write in the number 1, or just leave it off. It's your choice. But folks, that is the rate law. That is the answer. Okay? It says write the rate law expression. There it is. What is the overall reaction order? Remember, that means look at your entire rate law and add up the exponents. So there's a 2, there's a 1. This is overall third order. That's how you say it. Okay. And now let's look at this last question. Okay, we didn't do this last class, so I'm showing it to you now. It says, what is the value, meaning I want you to calculate a number. What is the value of the rate constant? Solve for a number for k. How could we do that? Given what we're given. Ideas? Plug in numbers. What numbers? Any of the lines. Pick any of these 3 lines. I'll just tell you, I always pick the first one just because I do. But you could pick any one that you want and just plug in the numbers. On the first line, the rate is 0.18 times 0.10. Don't forget to keep those exponents that you just solved for. Okay, what do you get? You're going to need your calculators a lot today, so you might as well have them out.
Ken, why don't you calculate it?
No.
According to my calculation.
I'll do a calculator here.
You don't feel like calculating? Then when are you going to use that phrase?
Never.
If you get a number, shout it out. All right.
No, I cannot ask you that.
There you go.
I'm staying after.
Okay?
Yeah. 18. That's it. Do the homework.
Try this one on your own. Go.
Don't you have homework?
Before I haven't finished the problem here, I just want to call your attention to something if this was troublesome at all. When you are finding the exponent for x, which 2 lines did you choose to compare? For x. Okay. 3 to 4. Well, going from 0.4 to 0.2, what are you multiplying by? 1/2. If that bothers you, if fractions make you nervous, okay, it's not going to change the way the problem is, but if that makes you nervous, then just go the other way. Go from 0.2 to 0.4. That's being multiplied by 2. This is remaining constant. What's this being multiplied by? 4. 2 squared equals 4. If you ever come across a situation where you've got a fraction, if you don't like that, then just go the other way. It's not going to change anything.
Stop it.
Ladies and gentlemen, let's talk about units.
That's the word.
Okay? And I'm going to test your algebra skills here. Well, here's the bad news. The units for k are different for every problem.
How?
Well, I'll show you. And you're going to have to figure it out. Here's the thing, okay? Although k, that rate constant, may have different units for every problem, the rate itself does not have different units. Now, think about it from like a physics perspective. When you write a rate or a speed in physics, what's a really common unit that you use? Okay, meters per second. Great. Well, we don't use meters. We're not measuring distances in chemistry. So the rates are always going to be in units like this. Molarities per some unit of time. Could be seconds, minutes, hours, whatever. I'm just going to write the generic term time. Molarity per time. I am going to rewrite the rate law I have just found. Instead of putting in variables, I'm going to put in the units for each thing. Rates are in units of molarity over time. I don't know what the units are for K. What do brackets mean again? Okay, molarities. Okay. This molarity is being squared. And this is a molarity to the first power. I'm just going to simplify this a little bit. Do you all see? I've just simplified it. I haven't changed anything. Okay, I just combined these two together. Now let's think basic algebra here. How could I isolate K? Okay. Sounds good. Those are gone. How can I simplify this a little bit? What gets canceled out? Okay, the top M, and then this becomes... So the units for K, I'm going to write it in multiple ways. All of these are acceptable. You could write it like this. This is sort of a clunkier way to write it, but it is still correct. You could write it like that. You could write it like that. You could write it like this. It's totally up to you. All three of those mean the exact same thing. They are all equally correct. You choose which one you like. I'm going to pick this last one, but it's your choice. Now I'm going to attach them to the number. Yes, ma'am?
So then how do you know what form of time is used?
Sometimes the question will tell you that it's in molarity per second. Sometimes they'll say it's in molarity per minute. But if they don't tell you, then you can just use the generic word time. Okay. And guys, I'll tell you that on a real AP exam, and thus on my tests as well, getting the right number and the right unit are two totally separate points. Okay? Because the units are different for every problem depending on what these exponents are. Since they're different every time, usually on most free response questions, just having units is like 1 point. Because this is a little more challenging, I might bump that up to 2 or 3. Okay? Because you have to figure it out for every problem. And let me just say one more time in case you missed it. Alright? K is going to have different units for every problem. But rate will always be the same. It will always be molarity per some unit of time. Sometimes they'll tell you it's seconds or it's minutes. Sometimes they won't. Okay? If they don't, then you can just use this generic word, time. We're going to get some more practice with this. There are some problems in your problem set that ask you to do nothing more than figure out the units. Okay? There are some questions where they don't even ask you to find a number. They just want to know what the units would be. Okay? So we're going to, all through today, I'm going to give you some more practice with figuring out what the units would be for some rate constant. Okay, if you would please, take out a copy of your equation sheet. Folks, on your equation sheet, I want you to find a section that says thermochemistry / kinetics. If you can't find it, it's probably on the other side.
I can't find it. Right here. Okay.
most of this section, the equations there, are for thermochem, but look to the bottom of that section. The last 3 equations in this section are for this chapter. They're for kinetics. And we're going to use some in just a second. Now, before I start into this next section, I want to preface this by just saying you're going to be confused. Okay? Let's just accept it. Some of you may not be, and that's great, but I guarantee, I would imagine that most of you probably will be confused, but by the time I wrap up today, it will all make sense. Do you trust me? Okay.
I'm about to die.
I promise you will not be confused when you walk out the door. Here we go. Okay. If you say that a certain reaction operates under first order conditions, anytime you hear the word order, I want you to think exponent. So if I say something is first order, all that means is that's a rate law that has an exponent of 1. Okay? If what's written here in the middle is confusing to you, I mean, this is just the way we calculate any rate. But if it's confusing to you, cover it up. Here's a rate law. Look on either side. If something is first order, that's what its rate law would look like. Okay. Remember that I said to you when we started this chapter, those of you that are familiar with calculus are going to see some connections. You're going to start to see some of those connections today. This regular old rate law that we just used in our last problem, that's called a differentiated rate law. Sometimes you will be asked to write what's called an integrated rate law. If you are dealing with first order data, remember, all that means is a reactant that has an exponent of 1. This is what an integrated rate law looks like. Don't freak out. You don't need to memorize it. It's on your equation sheet. It looks a little different. I've just rearranged the equation. But folks, I want you to look at your equation sheets. It is the first of those 3 equations at the bottom. Can you see? Look up, look down, look up, look down. Can you see how it's the same equation? I've just rearranged it, that's all. And there's a reason why I've rearranged it. Okay? Let's just get our bearings here. What's LN? What does that mean?
Nitrogen.
Okay. What do brackets mean?
Molarity.
All right. This is the same K we were dealing with up here. It's the rate constant. This lowercase t stands for time. We didn't have time as one of our variables up here. Okay?
Rate.
So this is a little different, but we didn't have time isolated as a variable. It was part of the rate, but we didn't have it as its own isolated thing. Here's a natural log again. Here's a molarity again. What does this little 0 mean? Original, initial. Ladies and gentlemen, this is the concentration of reactant A at time 0. The starting concentration. If this is a starting concentration, what do you think this one is?
Oh, the end concentration.
Yeah, an end, a final concentration after some time has gone by. Okay? Now, I rearranged this equation from the way it's written on your equation sheet for a reason. Because, written like this, it's easier to see it in a linear form. Okay? If you have the notes, circle this statement, draw exclamation points and stars all around it. It's important. And let me tell you what a problem will look like that's going to address this situation. Let's say, and you will have problems like this on in your problem set. You're given a table of data. Just times and molarities. I want to point out, first of all, that is not the same kind of data you were given a couple of slides back when we were doing some practice problems. What kind of data was in that table? You had molarities, but what was on the far right-hand side?
Reaction rate.
Rate, speed. This is not what you're given here. You will be given a problem where you're given times and concentration. And maybe the question says, is this data first order? Yes or no? Prove it. Here's what you're going to do. You are going to plot this data on a graph, and we're not going to be like plotting things with graph paper or any of that. No. Doing it all in the calculator. If you put time on the x, and not just concentration, but the natural log of the concentration on the y, look, y equals mx plus b. If your data comes out to be a straight line, which it won't always, but let's say that it does, then you say, okay, this must be first order data. It's not zero order. It's not second order. It's not third order. It's first order. Which means you may use this equation if you need to. If you have second order data, you can't use this equation because this is for first order only. Okay? Now, what else comes up is the concept of half-life. Let me refresh your memory. This is a topic you covered in Chem 1. Half-life, first of all, is a length of time. Could be in seconds, minutes, hours, days, fortnights, whatever. Okay? Some unit of time. It's the time it takes, in this case, for a reactant to decrease by half. If your initial amount is 500 grams, remember, as a reaction goes on, reactant is disappearing while product is appearing. If I started with 500 grams, how long would it take to get down to 250? That's a half-life. And that's its variable right there. This is the same thing it's always been. This is a rate constant. Okay? I'm sorry to say this is an equation that is not on your equation sheet. I'm sorry to say that. Okay? But I want to just point something out to you, because I think it is kind of interesting. If we're dealing with first order data, look at this equation. Does the length of the half-life, does it depend on the initial molarity at all? Is that part of the equation? It does not. Half-life does not depend on concentration. Just wanted to point that out to you. So, let me sort of bring this home a little bit for you. We're going to do this practice problem together. The question says, a certain first order reaction, stop right there. They are telling you right off the bat that this is a first order situation. And in my mind, I think, okay, what are the equations that are available to me? Here's the first one. Here's a first order rate law. First order meaning it has an exponent of 1. I might use that one. It's first order, so I could also use the integrated rate law. That's available to me. And have a half-life reaction as well. Okay? So I haven't even read the problem. I'm just saying, what are my options? A certain first-order reaction has a half-life of 35 minutes. Well, since they've said the term half-life, I'm probably using this equation right here. Calculate the rate constant, meaning find a value for K. Can I do that using this equation right here?
Yeah.
Yes. Okay, let's do it. 35 minutes. What do you get for K? Give me a number. Point.
0.019.
Okay. Tell me what the units would be.
Meters per second.
No. Look at this equation. This is a number that does not have units at all. 1 over minute, or you could write it like this. Okay. Great. There's our answer to letter A. Quick and easy. Let's jump to letter B. How much time? Stop right there. Don't read any further. How much time? I'm solving for a time. Is time a variable in this equation?
No.
Nope. Is time in this one?
Yeah.
Okay. So its time is in this one as well, but this is a more specific time, so probably not going to use that one. Let's go with this one. How much time? That means that is my unknown. Is required for this reaction to be 65% complete. Okay, well, let's look at this equation and decide what do we have, what are we missing. T is my unknown. Do we have a number to plug in for K? Yeah, we just solved for it. The issue is what to do with these guys. If you see a percent symbol, what do you think is a really easy number to start with as your initial concentration? How about 100? Okay. Now don't immediately think 65 is what you're going to plug in here. Think about it for a second. If you start with 100, let's call it grams, just to make this a little easier. 100 grams of reactant. The reaction is 65% done. How much reactant do you have left over? 35. Now let's plug in the numbers. Natural log of 35 equals negative 0.0198. Use T. Get for T. 53? 53 what? Seconds, minutes, hours, days? Minutes. Okay. Now, let me just say something here. You don't have to start with 100. If you don't like that, you have options here. I just choose it because to me it's an easy number to start with when you're thinking about percents. You could choose 10. If you had 10, what would this be?
3.5.
3.5. If you didn't like the number 10 and decided to go with the number 1, what would this be? 0.35. Okay? And because that initial half-life was given in minutes, that means everything for the rest of the problem will be in minutes. Okay? So, again, if you are told right off the bat, this information is zero order, or first order, or second, I would recommend writing out the reactions, or I'm sorry, the equations that are your options, and decide which one is the best one to use.
A reaction can really take that much time.
Yeah. Some reactions are very slow. Folks, what if it's not first order data? What if it's second order data? Order, remember, just means the exponent is a 2 now. Okay? If you are asked to write the integrated rate law for something that is second order, this is what it looks like. Don't memorize it. It's on your equation sheet. It's the second equation on there. Again, it's written a little differently. It's just rearranged, but it is there. No natural logs. Now we've got inverses. Okay, but the variables are the same. This is still a rate constant. This is still time. Okay. And the reason I write it that way is so you can see the line equation. If you have the notes, circle it, draw exclamation points, stars all around it. That is a very important statement. Okay, let me say one more time what these problems are going to look like. Let's say again, you are given a table of data like this. Times, concentrations. And now the question says, this data could be first order or it could be second order data. Prove which one it is. Okay? Well, you think to yourself, okay, well I remember what the plot is for first order. Time is on the x. Natural log of the concentration is on the y. Does that look like a straight line to you? No. What does that mean to you? If that graph on the left is not straight, that means it's not first order. Okay? So you say, okay, well then maybe it's second order. So you try this. Time is still on the x, that doesn't change. But what's on the y now? Not natural log of concentration, but 1 over. Is that line straight? Yes or no? Yes. What does that mean? That the data is second order. And that means you have different options for equations. Okay. You might use the regular old rate law, which would just be rate equals K times your reactant squared. You might use the integrated rate law. You might use the half-life equation, which I'm sorry to say is different for second order data. Okay. By the way, I know that none of you are believing me when I tell you that this chapter is so easy. I know that no one is believing me right now. I promise it's easy. Just wait for it. Okay? If some data is second order, does its half-life depend on concentration? Yes, it does. But that's only if it's second order. Okay? And ladies and gentlemen, this is your final option. It might be first order data. It might be second. The only other option is zero order. And you might wonder, why did I put that one last? Why didn't I do that one first? Because this one comes up the least often of the three. That's why I put it last. Okay? If something is zero order, what's something raised to the 0 power? 1. How could you write this rate law in a much simpler way? Rate equals K. If rate equals K, what are the units for K? Molarity, over time. There you go. Okay. Here's what the integrated rate law looks like for something zero order. It's the simplest of the three. No natural logs, no inverses, just y equals mx plus b. Okay, I'll get to half-life in just a second. Okay. Just looking at this equation, in that y equals mx plus b format, if you were trying to test graphically whether this data was zero order, you'd still have time on the x. What would be on the y-axis? Just regular old molarity, just concentration. If that came out to be straight, then you'd say, yeah, that's zero order data. If you're asked to find the half-life, write this down. That's the half-life equation for zero order data. Now, I'm going to make your lives a little bit happier here. And I'm sorry I did not catch this earlier. The next 3 slides say more complicated reactions. Cross them out. I'm sorry, I thought I had crossed them out before. I apologize. Get rid of them. I'm not covering it.
We're not covering what?
This is a table from your book. If you want to write down the page number, it's on page 548. This table is your new best friend. Say hello. 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 I want to show you what good stuff is in this table. This table sums up everything I just said in one little place. If you are given a table of data, and we're going to do a problem like this in just a minute, you are ultimately testing for just 3 types. Is it zero order? If not, could it be first order? If not, then it must be second order. Those are your options. They've got the rate laws for each one. They've got the integrated rate laws for each one. This is my favorite part. Plot needed to give a straight line. Okay? Y versus X. Y versus X. Y versus X. It's got what the slopes are equal to. It's got the half-life equations. There's good stuff here. Okay? Don't worry about this statement. Just ignore it. Okay? Let's do a problem together. You will need your graphing calculator. And we are going to go through this together, step by step. Do not think that you are, super cool and jump ahead. No. Okay? If you don't have your graphing calculator with you today, please look on with someone who does. Okay? You are going to have problems just like this in your problem set. You are definitely going to see it on a test as well. We are given a table of data just like what I've been talking about. Times and molarities. And the question says, the first thing, determine the rate law. Okay, that means rate equals K times the reactant, but can you just look at this and know what the exponent should be? I can. So here's what we're going to do. We are not doing hand-drawn graphs. We're going to graph this in our calculators. Okay? Let's test for the simplest type first. Let's test for zero order. What is on a graph for zero order? What's on the X? Time? What's on the Y? Just molarity. Okay? So here we go, ladies and gentlemen. On your calculators, I want you to push this little button that says Stat. Edit. In L1, which just means list 1, I want you to enter these times and put these concentrations in list 2. Look up when you're finished. Next, I need to see these points plotted out. So go to second y equals stat plot. Okay, second y equals. Open your first stat plot. Make sure that it is turned on and not off. Okay. And in this section that says type, I would recommend clicking on the one that has all the dots connected with a line. It's the second one, top line, middle. Okay, doesn't really matter, but. And then for X list, guys, that means which list do you want for your X values, and which one do we want?
L1.
L1. Most of you, it defaults to that anyway. And on the Y list, which list do we want?
L2.
L2. If yours doesn't say L2, like mine doesn't, I'm going to hit second and the number 2, and that should pop it up. The fastest way to see these plots on your screen is go to Zoom. Scroll down to number 9, Zoom Stat. Hit enter. Do you see points on your screen? Ladies and gentlemen, do those points look like they are in a straight line to you?
No.
They don't look like they're in a straight line to me either. What does that mean?
It's not.
Reaction.
It is not zero order data. Okay, fine. Let's now test for the next one. Let's see if this is first order data. Go back to stat.
Stats.
Click on edit. And ladies and gentlemen, this time the easiest way to do this, go over to L3, list 3. The fastest way to do this so you are not entering number after number is to scroll up to the very top so that L3 is highlighted. Okay? Fastest way to do this so you're not typing in all these numbers. First of all, what do we want to graph to test for first order? We want time on the X, but what on the Y? Natural log of everything in that list. So with that L3 highlighted, type in ln, natural log, of L2. Everything in list 2, which is second and the number 2. Hit enter. You should see numbers like this. Negative 4.135, negative 4.2, negative 4.343, yes? Are we seeing numbers like that? Okay. Let's see what the points look like. Go back to your stat plot. Second, y equals. Open up your first stat plot. What's the only thing you want to change?
L2 to L3.
What the y list is. We want to keep the x list the same, but in the y list, I'm going to put list 3, second, and then the number 3.
It's still
Zoom,
not straight.
stat. Do you have points in front of you?
That's pretty straight.
Do they look straight?
No.
Perfectly straight?
No.
No. So what does that mean to you?
It is not first.
It is not first order. It wasn't 0. It's not first. What's the only other option?
Second.
It must be second. Okay? If this were a test question, I would not waste your time graphing this. You know it's going to be second. But I want to prove it to you. Go back to stat. Edit. Go over to list 4 this time. Go all the way up to the top so L4 is highlighted. To test for second order, what do you want on the y-axis?
1 L2.
1 over these concentrations. So 1 divided by everything in list 2. Second, and then the number 2. Hit enter. Do you have numbers like 62.5,
Yes.
66.66? Yes? Okay. Let's go look at it. Open up that stat block one more time. What do you want to change?
L4.
The Y list, change it to L4. Zoom.
That's not.
That's straight.
Do they look straight now?
Yes.
Kind of.
Kind of. They look pretty straight to me.
May I get a drink of water, please?
You're wasting class time.
So, what's the moral of the story? What can you tell me about this data? It's second order. Determine the rate law. Okay, fine. That's easy now. Rate equals K. You don't have to call it A because we actually know what the reactant is. To the second power. Okay. Determine the rate law. Okay, check. We got that. Determine the integrated rate law. Okay. I'm going to have to write kind of small here. Equals KT plus. Make sure you put that little 0 next to it to denote that that's an initial concentration. Yes, it does. It's a positive K. If you're unsure, look at your equation sheet. It's there. So determine the rate law, check. The integrated rate law, check. Got it. And this is the trickiest part. They want a value for K. Well, ladies and gentlemen, I want you to put your thinking caps on. Look at the two equations that I now know we can use, the ones I've written in yellow. Look at the information given. Think about the graph that should be on your calculator right now. How could we find a value for K? Throw out some ideas. Oh, see, you guys are overachievers. I was hoping for some lesser ideas. But that is correct. On your calculator, you should have a graph that looks something like this, something with a positive slope. Okay? Look at the integrated rate law. If you ever forget, what is the relationship of this line to slope? Y equals M. Slope is K. And folks, you have some options here. For those of you that know how to use your calculator to find the slope from a set of data, great, go for it. If you don't, or you don't have your calculator, how could you find the slope just from this table of data? Okay. That's using your calculator. Okay, if you don't have a calculator. Okay, change in Y over change in X. Well, what are the best 2 points out of these 5 to use if you're calculating slope? First and last. Okay? Tell me why what I'm writing here is incorrect. So don't write this down. Why is this wrong? Why is that wrong for the change in Y? Isn't that this minus that? What's wrong with that? Time was on the X. What was on the Y over here? 1 over the concentration. This is not correct. This is correct. change in time. Put that in your calculator, you're going to end up getting a number something like this for the slope. The slope is k. What are the units for k?
Do we have to
If you're
calculate?
unsure, I would recommend going back to your regular old rate law. Use a little algebra to figure it out. Remember, the units for rate are always the same. They told us it was in seconds, so molarity per second. This is how I'm going to write it. You may write it differently, but this is what I'm going to do. Okay? Figures. Okay. So, that is where I'm going to stop.